This is a recording for vector integrals, talking about how to integrate vector functions and what you should expect out of them. And this first part we're going to go through is just the computational background, and then we'll also look at a visual in a minute. So the first thing is the definition of vector integrals is just the integral of r of t dt, where r of t is a vector function. You can think of that as the integral of the components, this f of t, g of t, h of t for the I, j, k components. And I'm just going to integrate each of those vector functions right there. So integrate the f, the g, and the h just like you normally would in, say, Calc 2 class. And then the result that comes out is just the components now of this vector integral function. So big F, big G, big H. Don't forget, if it's not bounded, you got to add in that plus C1 or C2 or C3 for each of these functions. So I'm ending up with just this big F, big G, big H for the I, J, K components, and then that plus C. And you can either write the plus C with each of the components, or sometimes we just combine those together into a plus C vector at the end, where that C vector is just the C1, C2, C3 components from each of those. So a lot of times that's the notation that people use with that. But you're strictly just integrating each of the separate components. So we'll go ahead and run through an example here in a second. If you have a bounded integral, then you're essentially going to do the same idea, integrate each piece, but then plug in the bounds and subtract. So exactly the same thing that you do in a Calc 2 setting with real functions. But this time you're plugging into a vector function. So you plug the upper bound b into that integral function, big R, and plug in a, same thing, into big R, and then subtract. And so you're subtracting two vectors. What you should get at the end is a vector. And that big R is, again, just that standard notation of an antiderivative of little r. So that's what's going on with those guys. We'll go ahead and do a computational example, and then we'll look at a visual of really what's going on with this behind the scenes. So here's our example. We're going to do the let r of t be cosine t, sine t, and t over 2 for those components. And we just want to find the general integral of r of t and also the integral from 0 to 2 pi, so that bounded integral. So we're going to look at both of those. The first one here is basically just integrating cosine, sine, and t over 2. So integral of cosine, remember, is sine t. Integral of sine is negative cosine t. And integral of t over 2 is just t squared over 4. So each of those components. And then I tack on that plus c vector at the end, because this could shift positions or whatnot. The bounded integral, I'm just going to take that same integral function and then plug in the bound. So I plug in 2 pi to each of those components, plug in 0 to each of those components, and then subtract. So sine 2 pi is 0 minus sine of 0, so that gives us 0 minus 0, or just 0. Negative cosine 2 pi, that's going to be negative 1. And then minus and negative, so that'll be plus cosine of 0, or plus 1. And that again is going to evaluate to 0, so negative 1 plus 1 is 0. And then this 2 pi quantity squared is really just 4 pi squared, and then divide by 4. So we end up with pi squared, and then minus that 0 again, so just pi squared in that case. From 0 to 2 pi, the value of this integral is just 0, 0 pi squared. So again, out of that vector function, if we integrate, even if it's bounded, we should get a vector back out of that guy. Now really, these are not too hard computationally, as long as you know how to do the integrals. So you're just basically doing the 3 separate integrals, plug in the bounds if it's a bounded one. But really what's going on behind the scenes is this limit definition of our integrals. So this integral from a to b of r of t dt is the limit as n goes to infinity. So I'm taking infinite number of components here of the sum of these r of ti. So this is the same type of definition you would see in a standard Calc 2 regular function definition. The sum from I is 0 to n minus 1, that's sort of like a left-hand sum, times this function value times delta t. So, and then we add those up and take the limit as we take more and more components, or smaller and smaller values of rectangles or whatnot, where that delta t is b minus a over n. So in the 2D version, these can be interpreted as rectangles with that width delta t. The vector function, we're not really going to get rectangles out of these guys. We're going to be adding up vectors. So here's the interpretation you should get with that, is that we're taking each of these r of t's, or r of ti, for I is 0 to n minus 1. And these r of ti's are just going to be vectors along that function, but then shortened by this delta t. So we're just going to sum up the direction vectors from r that have been shortened by this factor of delta t. And then we're going to take the limit as we add more and more and more vectors that are smaller and smaller. So as n goes to infinity, that delta t gets shorter, and we're summing up more vectors but shorter vectors. And so we'll take a look at what that picture looks like. So here's what this type of thing looks like, and I'm going to use, say, just a small number of vectors at the beginning, maybe just like 12. So here's our vector function, cosine t, sine t, t over 2, and that's this dotted line that you see right here. So we expect that to be a helix that's going around the x and y with that circle. So cosine and sine gives us that circular motion in the xy direction. But then this also moves up with that z being t over 2. And so we'll get some sort of helix that looks a little bit like that going along that dotted line. Now these small black lines that you see coming out are the position vectors at all these positions. So in this case I'm using 12 of those, so 12 little arrows going out toward that position, but then these are going to be shortened by that b minus a over 12, and in this case I have 0 to 2 pi, so again just that 2 pi minus 0 over 12, and shorten the vector by that much. So those are what I'm going to add up, and when we add those up, you add up vectors from tail to head, tail to head, tail to head. So if I go ahead and show these arrowheads, we're just adding up those vectors, tail to head, all the way up. And each of these corresponds to these position vectors over here, just moved around. So remember, vectors you can move around wherever you want, but if you add them up, you have to go from the tail to the head, all along those guys. So you'll notice this, if I go ahead and rotate this guy, this red vector pointing along the x-axis, same as this one pointing in the direction of the x-axis. This purple one that's pointing toward that negative y direction, same thing as this purple one pointing toward the negative y direction. So all of these in this left-hand r vector function have just been rearranged to go along this integral vector function. So what comes out is basically this integral vector function just tracing along these vectors that get added up. Now if I plug in the bounds, we just go from this initial point to this final point, so that b minus a is just subtracting the end point of this vector and the start point of this vector. So that's the resulting vector that comes out, that 0, 0, pi squared. In this case it's approximated because we're only using about 12 of these, so they don't come out to exactly 0 on that guy. But as you use more and more of these, this will get more and more accurate. So if I go ahead and increase that n to, let's say, almost 40, about 38 of these, notice that b minus a over n gets shorter. That gets smaller, so these vectors are shorter. So I'm adding up more of these, but they're smaller vectors, and so we just continue along this path of the vector function that I integrated. So this is the integral vector function pictured over here, that dotted line, which would be that sine, negative cosine, and then that t squared over 4. But this time what I'm going to do is just use about a lot more vectors, so about 38 of these guys. And if I hide the arrowheads, you'll see, this is a pretty smooth curve that approximates that actual vector integral function. And then if I wanted to plug in a bounds, again I'm just going from one point on this guy as my endpoint, that value of b, and then minus that value of a, and the result is just the vector that goes between those two guys. So in this case, that'd be the 0, 0, pi squared for this one. So that's what's going on with picture view of integral functions. If you have any questions on that, feel free to ask me either in the forums or when we meet in class next time.